Welcome back everyone. So we are studying topological phases of matter. In this week we are studying model Hamiltonians. So we have gone through two sets of model Hamiltonian for 1 dimensions and 2 dimensions, and we have also looked into relevant materials or other toy models. Now we will be more into materials. So one thing we realized by now is that it's not any 2 by 2 Hamiltonian is good enough to give us a topological insulator. We need certain criteria, and the criteria that we figure out is that D1, D2, D3, which were the off diagonal and the diagonal term, but which has a opposite sign between the diagonal component. So this 3 component makes a traceless Hamiltonian, and all 3 has to change sign. So if they all change a sign at the same point, you have a Dirac cone. That those are also topological semimetals, because at the Dirac cone your Berry connection diverges. So those are the singular point, and also the second case we studied is all the 3 D1, D2, D3 has to change sign, but at different k point. Then we have a topological insulators. And the set of Hamiltonian we studied is that the off diagonal terms, which are written by D1, D2, should have this sort of form, such that they will vanish at the high symmetry k points. So it is not that this form matters, it is the fact that they all have to vanish at the same point at the high symmetry k points. And these were the forms which were sort of trivial form, which vanishes at gamma point, pi point, pi 0 point, 0 pi point. Those are the choices we made. And the third one is D3, which will change sign in some ring that will encircle those points where D1, D2 goes to 0. Okay. And obviously they are interchangeable because there is a SU2 symmetry or a O3 symmetry, in which what you call D1, one can call it D3, and then you get a cyclic rotation, right. So it is not the term that is associated with these Pauli matrices is important, but as long as there is a rotational symmetry and these criteria are satisfied in whichever term among the D1, D2, D3, we have a topological insulator. So these are the common materials, I would rather say even common platform on which topological materials naturally arises or can be engineered, and they turn out to be graphene and Rashba spin orbit coupling, I would say Rashba is a special case. Even a spin orbit coupling of LS coupling, JJ coupling would suffice in many cases to give a topological insulator, and Rashba being a special case in which you will see the terms will look very much like these things. Okay. And for graphene also it may not look like this as for the D1, D2, but eventually we will find that there are symmetry regions for the dispersion which will vanish at high symmetry k points. And the third one is tight binding hopping between even and odd symmetric orbitals. So even means S, D orbitals and odd would mean p f orbitals. Okay. We will discuss this one in great details. This is also with sufficient details, and this one we will lay out some tight binding model with even and odd orbital, and especially I will take S and P to show that they give this sort of term in the off diagonal part of the Hamiltonian, so that they will vanish at the isometric k points. And then the remaining part will be to engineer a D3 that will change sign in these materials to garner topological insulators. So, graphene, it's a honeycomb lattice, okay, and a honeycomb lattice is a hexagonal lattice which is not a Bravais lattice, and you have a Bravais lattice is when at all the lattice points you have the same atom, and you can see that you do not have the same atom. This environment and these environments are different. So, what we generally then do is that we define a Bravais lattice which will be triangular lattice, and then treat the other one as basis. And we will call this as A basis and blue one as B basis atoms. Okay. And the lattice vector would be A1 and A2. So, I should give the reference. RMP, Review of Modern Physics, okay, and A2 from here to here is this, and the reciprocal lattice vector would be B1, B2, which are, so if I think of kx ky is like that, so B1 B2 will be along these two directions. Okay. And the high symmetric k points are at these vertices. It turns out k1 and k2 are the important points, which is this point and this point, and we will come back to why they are important. We will see that these are the points where the band dispersions will vanish. So, now we want to write a tight binding Hamiltonian with nearest neighbor hopping. So, these are the nearest neighbors. Take any site which is A site, and you have, okay, the we will consider this as B. So, the nearest neighbor is the different atoms that sits. So, the nearest neighbor term will give a off diagonal term, and the nearest neighbors are these three. We will talk about next nearest neighbor later. So, with that we write our Hamiltonian as minus T C I A dagger C I B. So, I stands for the unit cell. So, within the unit cell different, actually the unit cell as well as the nearest neighbor. So, let me do it J, okay, and plus Hermitian conjugate. Right now I am not including the second nearest neighbor, which would be hopping from A site to A site and B site to B site. We will include it later. Right now I am interested in getting the off diagonal term in the form that we wanted. So with the Fourier transformation, this will become like this, where these are the three hopping terms. With this is the block phase for delta 1, delta 3 and delta 2. Alright. Okay. And I generally call it minus T Fk, where Fk is this part. So turns out I set A, the lattice constant, to be 1. Which can be easily obtained by substituting this nearest neighbor, which we gave here. All right, and now to represent this Hamiltonian as a matrix form, we take this as a spinor. Alright, so then the Hamiltonian is written in this spinor basis, which will be alright. This is our standard notation. So D1 is real part of epsilon AP. That will just be minus T cos ky plus 2 cos ky by 2 and D2 will be imaginary part of AP, which is equal to minus T. This will be sin ky minus 2 sin ky by 2 right. So I take the real part and imaginary part, and I take the real part and imaginary part. This remains. Okay. So now what is interesting about graphene lattice is that, so T is a normal kind of a overall time scale here, temperature scale here. Sorry, T is a overall energy scale. So it comes out from the Hamiltonian. So the question is whether these terms would vanish at any given point together. Although it does not look like from the face of it, but if you look at these high symmetry k points, which are this point and this point, okay, this and this point, and these are the k points. So what we find is that D1 and D2 goes to 0 at k and k prime. Let me call it k prime. So this you can check easily. And not only that, it's a good idea to just do this expansion as we did earlier. Let's call it Q, and what does it look? And let's do it the other way, k prime plus Q, and I will give it as a homework to do. You do it first in the tight binding way, and then we look into the Taylor expansion way. And obviously the first term I didn't write, and this one goes to 0, and you will have a similar term. This is the velocity, right? So now what do we find is that will be minus 3 by 2 t, and okay, some other factor which are a by h cross, that will come in terms of defining this as a velocity operator, and then it will be qx minus I qy, or right, I think. So which says, and let me write it as Vf qx minus I qi, where Vf is equal to 3t by 2h bar a, which is of the order of 10 to the power 6 meter per second, and that's like c by 10 to the power 3 speed of light. So this is very high for a quasi-particle electrons in a lattice, and T is of the order of 2.8 eV is the value that we obtain by fitting to the density functional theory and experiment. So you see that these electrons near this k point does have a relativistic like dispersion which is linear. So this one can be written as like a relativistic dispersion with linear dispersion in for sigma x and sigma y with velocity that's very high. So we are actually in the relativistic limit indeed. Okay. And AB around k point, k prime, will be Vf Qx Cx, instead of minus you will have a plus. So H around k prime star. Okay. And so I have just reported you these dispersions. This is how, if you plot it, Okay. So, if you plot it in the kx ky plane, you do see that there is a full dispersions all over, and except at k and k prime point, you do have a linear dispersion and all over with a uniform velocity along kx and ky. Okay. So, we have now achieved the sort of dispersions we wanted, but this remains, and there is no d3 term. If you take the second nearest neighbor hopping, you will get a same term for hopping between in the diagonal term for A and B sublattice, and same term does not give us d3. It is the difference between the diagonal terms gives us d3. So, you will find that if you take A to A or B to B hopping, you do not get a term that is going to give us the topological insulator, it is just going to shift things around. So, this existing graphene lies at a topological phase. So, graphene gives gapless Dirac cone at k and k prime. D3 does not exist actually. It is actually prohibited by symmetry, which we will talk about later. So, it is 0. And another thing for k dot p model. So, now because graphene now has two Dirac cone which are not same, as we just showed that this Dirac cone and this Dirac cone has ky or qy directions opposite. So, they are sort of going in different directions along ky, which are called chirality. So, we have two chiral state, and this k and k prime are also called valley or valley degrees of freedom. So, to write a k dot p model at the low energy, we do have to now include CKA, CKB. Now, I want to do it around K plus QA, K plus QB, and we also need to include the other value K prime plus Q, K prime plus QB. Two sublattice from the real space and two valley to get a continuum model, k dot p model around the two Dirac points which are not same. And then the Hamiltonian will be a 4 by 4 Hamiltonian, and each one will be a 2 by 2. So, that gives us q dot sigma 0 2 by 2 q dot sigma star. So, you see that we do have two Dirac cone which are split in momentum space, but they are Dirac cone, they are not wild cone. Why? Because for the wild cone, recall that they occur at non-high symmetric k points, but here this is the Dirac cones are happening at the high symmetric k points. So, these are Dirac cone, not wild. Okay. Alright, so the question is then, how do you generate a D3 term which can gap out this k points, these Dirac cones, and give us a topological insulator? So that will be the next class, but before that I want to talk about two more quick things about getting this sort of band degeneracy at high symmetric k points. Another one is Rashba spin orbit coupling. So it is a spin orbit coupling, but it is a different mechanism. So rather what we have is spin momentum locking, and we call it spin orbit coupling, although it is not orbital, but the mechanism is very similar. So if a system has no inversion symmetry, and before we learn what is inversion symmetry, so let me give you the example, which are that 2D surface state interface or any 2D materials, or any non-center symmetric material, or even asymmetric quantum wells. So something like this, so the material, if you look at the upside and downside, they are not necessarily the same. So this material by definition breaks the inversion symmetry. So if I have a inversion symmetry breaking material, then, and there are atoms sitting here, so all these points, there can be off center atoms between them. So an electric field is allowed, electric field breaks inversion symmetry. Electric field or electric polarization is allowed when inversion symmetry is lost. Now the electric field can be externally applied or internally generated, because your atoms, the positive charge density and negative charge density center can be off center from each other, giving rise to intrinsic polarization. Sometimes they are called ferroelectrics. Okay. So it can be intrinsic or extrinsic. So now if I have an electric field and without losing generality I have assumed the and the inversion symmetry is broken along z direction. So I have assumed the electric field will be along z direction. But let me start with a little more general electric field. If I have an electric field in a material and a conduction electron of velocity b, let us say it is moving like this with velocity v, So, in the moving frame of reference of the electron, the electric field, because if it is in the relativistic limit, so moving very fast, I'm gonna sees the electric field as magnetic field, okay, and let us call it, it is the same mechanism of the spin orbit coupling as well, and let me call it effective. The normalizations do not matter, right, maybe 1 over c square if you like, and it will be, if V is this way, then magnetic field will be perpendicular if V is this way, okay. So now these electrons are in a band, so these electrons velocity are nothing but the effective band velocity, which we can write it like this. With respect to some point, which we set it to be k equal to 0, like this, right. So that means the effective magnetic field is k dependent, and let us call this as some velocity, and let us set it to be Fermi level, okay. Or let us even assume them to be, this can be slightly misleading, but let me, alright. Let us assume them to be even uniform, otherwise you will have little more general spin orbit coupling that we can derive from this expression. This is more of general. Let us assume, let us take a uniform velocity along all the directions, and then electron also has spin. So the spin sees this magnetic field, and then there will be a Zeeman coupling, and this magnetic field is momentum dependent, where the spin of the electron is this. Okay. And now let us put all these terms. So we will have sigma dot k cross E in all the coefficients constant I have taken here, and these coefficients we generally call Rashba spin orbit coupling, and because this is a triple product, so we can always choose a rotate them, and electric field we set it to be along z direction. So okay, let me do one more step. And along z direction. So generally we don't write it as along z direction because it's sort of obvious. So if I have an electric field along z direction, so electron is moving in kx ky plane. So these are only defined in the kx ky plane, and this is sigma x sigma y. So now we put everything here. Rashba spin orbit coupling. So, in which we have chosen the basis like this. So, it is a coupling between up and down spin and which is k dependent, and this Rashba spin orbit coupling, and the full Hamiltonian then would be some quadratic band without the spin, and then we will have Rashba spin orbit coupling. So, the important thing is that this also vanishes at k equal to 0. Spin orbit coupling vanishes, or the splitting vanishes. So, if I start with up and down spin degenerate band with spin orbit coupling, it will split into this will be say up spin and this will be down spin, and the splitting goes to 0 at k equal to 0, and you do have a band degeneracy. Okay. So, this is very different splitting from Zeeman coupling, because here the magnetic field is k dependent. So, this also turns out to be a very important term, because it gives exactly the term that we need. Maybe kx is coupled to now sigma y and ky is coupled to sigma x, but that does not make much of a difference. And the third one is tight binding dispersion between even and odd orbitals. So, the reference for this is okay. Let's take s orbital and px py orbital, or even pz orbital. Let's start with even pz. Okay. Let's take some sort of a square lattice, or even 1D if you like. So, I have some s orbital and I have some pz orbital, and I am assuming this to be along z direction, which is here. So, the important point between a even and odd orbital hopping is that the hopping, if I take to be t, the hopping in the minus x directions will become minus t. So, then will be t to the power I kz, and again I am setting the lattice constant to be 1 minus this will give us 2t sin kz. So, this is also going to vanish at all the high symmetric k points and eventually will give us a linear dispersion around those degenerate point. So, now generalizing this to more px py orbital, and you can generate kx ky and if necessary kz orbital and different lattices. So, the key point, and then one has to build on it and get the topological insulator. So, the key point of these 3 examples we gave is that we find 3 different mechanisms in which we have a off diagonal term which vanishes identically at high symmetric k points. In the next class, we will use this as to obtain topological insulators by gapping out those Dirac points. All right, see you in next class. Thank you very much for your attention.